So the third thing we ask about a function is its vertex. Where is its highest point, or where is its lowest point, or as you were saying before, where is the place where the graph changes from being increasing to being decreasing, or vice versa, where its slope changes from positive to negative, or vice versa. So you pointed out to me that on this particular graph, and again, this is the graph that has the equation y equals x squared minus 4x minus 21. You pointed out to me that there's one vertex, and it's down here at the bottom of the hill. So yes, for a parabola, there is always one and only one vertex point. That's the bottom of the hill in this example. Before we go any further, is it obvious from the form of this equation why the vertex is at the bottom of a hill instead of at the top of a mountain? How do we know that this parabola has a lowest point instead of a highest point? So for parabolas, for quadratics, one of the things that you learn about how to classify them is that this leading coefficient, the thing we called a minute ago, a equals 1 in this example, because that coefficient is positive, that means that this parabola, what we might say, opens upward. Right? It looks like a cup instead of a cap. Whereas if a was negative, then my parabola opens down. So those are things that you sort of learn about the graphs of quadratic functions back in an algebra or pre-calculus class. We don't really need calculus to answer those questions, right? So even before we do any computation, we know that the vertex of this parabola, because the parabola opens upward, the vertex is going to be a minimum. So maybe that's another way to think about, the vertex is a minimum if the parabola opens upward if the coefficient a is positive, and the opposite is true if a is negative. Opens downward, vertex is a maximum. Okay. But knowing that doesn't tell us the coordinates of this vertex. We have to find the coordinates in some other way. So let's think for a moment about how we might do that. Can you think, just based on knowing nothing else, what relationship do you think this vertex has with the intercepts that we've plotted here? You noticed about the intercepts that if I multiply the two x-intercepts together, negative 3 times 7, what do I get? Which happens to be y-intercept. Ooh, that's good. I wasn't planning on going there, but that's a really interesting observation. So how a math major thinks about an observation like that is, I wonder if that's always true for any quadratic function. If you would like, you can look this up, but it is in fact true. If I multiply the two x-intercepts, the x-coordinates of the x-intercepts, it's going to give me the y-coordinate of the y-intercept. This is actually true for every quadratic function. You shouldn't believe me if you're, go ask a math major friend of yours or something if they can furnish a proof of this. But yeah, this is true. So that actually is a really interesting connection between the three different intercept points that I have here. They don't quite get me to the vertex, but they do tell me something about the relationship between those other three things. What else? Is there something about the shape of this graph that could help us? One of the important things about a parabola is that it's symmetrical. It's symmetrical about its what's called the Axis of Symmetry, which is a vertical line that runs, sort of up and down through the vertex. So if I were to just kind of draw a vertical line here passing through the vertex, that portion of the parabola which is on the right side of that line is the mirror image of that portion of the parabola which is on the left side of that line, right? It's exactly the same on one side as it is on the other. And because of that symmetry, as you were just saying, the distance in the x direction between the vertex and each of the x-intercepts is going to be the same. So this vertex is going to be as far away from 7 on the x-axis as it is away from negative 3 on the x-axis. So this distance going this way is going to equal this distance going the other way. Right, so the vertex is halfway between the x-intercepts. So these distances are equal. All right, so how do we figure out how to go halfway in between? How do we split the difference between negative 3 and 7? What's the total distance from -3 to 7 on the x-axis? 10. 7 minus -3, right? So if that total distance is 10, how much is each of these green distances?
5.
Just cut that in half. So that must mean that the vertex is 5 units away from each of my two intercepts. And so the x-coordinate of my vertex would be -3 plus 5, otherwise known as +2. By the way, it's the same thing as the average of the two x-intercepts. It's another way to think about it. Average of the two x-intercepts. And you average something by adding them together and dividing the result by 2. 7 plus -3 divided by 2. That's going to be 4 over 2. That gives me 2. So if you already know the x-intercepts of a parabola, just average them together, and you get the x-coordinate of the vertex. And once we have an x-coordinate, we are kind of home free at that point. Because how do I figure out the y-coordinate that goes with that x-coordinate?
Plug it back into the equation.
Just evaluate it back into the function. F of 2. Right. We have this equation that relates x and y together. So if I know a value for x, that equation can tell me the value for y. Plug in a 2 for x, and then evaluate it out. So I get 2 squared minus 4 times 2 minus 21. That's 4 minus 8 minus 21. That's -25. 2 and -25. There we go. So that's what we do if we already know our x-intercepts. What if we didn't know our x-intercepts? Would there have been another way to find the coordinates of the vertex? When we did the quadratic formula before, minus b, so x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. We did a bunch of work for this quadratic. A was 1, b was -4, c was -21. And so we ended up with this 4 plus or minus 10 all divided by 2, right? All the algebra that we did a few minutes ago. But notice what this plus and minus is doing. Let me break this apart. So what I really have here is 4 over 2 plus or minus 10 over 2. Right? And 4 over 2 is otherwise known as 2. And 10 over 2 is otherwise known as 5. So another way to understand these x-intercepts is that they are 2 plus or minus 5. Well, plus 5 and minus 5 just means go 5 units. By the way, that 5 is this 5. Right? Go 5 units on either side of the value 2. And so that must mean that this 2 plays the role of the vertex. And if we trace that back through the quadratic formula, this 2 was this 4 divided by 2, which was this 4 divided by this 2, which was this minus b divided by this 2a. So just going all the way back through our quadratic formula gives us the reason why that trick works. Right? So minus b over 2a is the quick and easy way to discover the x-coordinate of a vertex. Minus b over 2a. And once I know minus b over 2a is the x-coordinate, then I just have to evaluate my function f at minus b over 2a to find the y-coordinate. So that's the quick and easy way. It doesn't require us to know the x-intercepts. It doesn't even require us to have x-intercepts, which is kind of one other surprising thing about this. It works regardless of whether your parabola even crosses the x-axis. So for quadratics, we can answer all 3 of these questions. When is the input equal to 0? By finding a y-intercept, setting x equal to 0 and solving for y. When is the output 0? So find the x-intercepts by setting y equal to 0 and solving for x. And when is the output highest or lowest? What we're doing here is finding what we would call a global maximum or a global minimum. Global max or global min. And for a parabola, this would be the vertex of a parabola, which is either located at minus b over 2a if you don't know the x-intercepts, or it's located at the average of the two x-intercepts if you happen to know them.